Hello, everybody. Today we're going to go through the lecture 9, which is the divergence and curl of electrostatic fields. So first, in this lecture, we're going to cover the field lines, flux, and Gauss law. So first, let's see what is field line. Let's begin with the simplest case, a single point charge Q situated at the origin. So now let's see if this is a point charge here, and if we want to calculate the electric field, we can use this equation, which is from the Coulomb's equation, and you will get it's 1/4 pi epsilon 0 cube over r squared, and the direction of the electric field is in the radial direction. So if you draw the E in the XY coordinate system, you will see the field lines looks like this figure A, because E is function of R. So 4 pi, epsilon, and Q's are all constant in this equation. So the only variable is R. So when R is greater, E becomes smaller. So we'll see when R is greater, for example, when R is here, E is smaller than when R is smaller. So in order to indicate the strength of the electric field, what we can do is we can draw vectors in this way. When it's close to the center, we draw long arrows, which means stronger electric field. When the position is further from the origin, then the arrow is shorter. So we can use the length of the arrow to indicate the strength of electric field. However, actually there's another way which is easier to indicate the strength of electric field, which is shown in figure B. In figure B, we use vectors or lines with arrows to indicate the direction of the electric field. And we don't have to make big arrows or small arrows to indicate the strength of electric field. What we can do is we can use density of electric field lines to indicate the strength of electric field. For example, if you look at some region which is closer to the origin, you will see the density of the electric field lines. It's more denser than if you look at some place which is further from the electric field lines, from the origins, then the density is lower. So when the electric field lines density is higher, then the electric field is stronger. When the density is lower, then it's weaker. And we call these lines to be field lines or electric field lines. Electric field lines. The strength of the field or electric field becomes the density of the field lines. So that's the connection between strength and density of electric field lines. The magnitude of field line is indicated by the density of the field lines. It's stronger near the center, where the electric field lines are closer together, and weaker when further out, where they have relatively far apart. So that's some definition or introduction of field lines. Now, let's see what features does field line have. So now let's see. First, if you have a positive charge, let's say somewhere here, the field lines will be something like this. So it's radially going out. And in the center, the density of field lines is stronger. When it's further, the density is lower. This is for positive charge. If it's a negative charge, the direction of the field lines are just opposite. So the field lines going to the center of the negative charge. So now let's see some features of the field lines. First of all, the field lines are always come from or start from positive charge. It goes to infinity or negative charge. And based on this feature, if you put a positive charge and negative charge together, what do the field lines look like? So we can see it in this figure. If you put a positive and negative charge, the field lines will go from positive charge to the next negative charge in this way. And the positive charges, as a positive charge has some field lines go to the negative charge and some other field lines go to infinity. For the negative charge, there are some field lines go into the negative charge from positive charge and others are from infinity. So this is opposite charges. If you have equal charges, then the field line looks like that. So all the field lines are either from the positive charge in the left or in the right. So they all go into the infinity. So so the distribution of field lines look like this. Okay, so another feature is field lines can never cross, because if you have some field lines, like let's say at some position here, if field lines cross, what does it mean? So field lines, if the two field lines cross in this way, what does it mean? It means you can sum the two electric field, let's say E1 and E2. If you do a sum of the two electric field lines, then the sum goes in this direction, which is E. So that means the field line, the final field line is going down. It's not going in the direction of E1 or E2, but it's going to the direction of E. So if the field line cross, then it will become let's say combined or merged into a sum of the field line, and it becomes a new field line. It's so they don't cross. So with all the features in mind, it's easy to sketch the field line of any simple configuration of point charges. For example, if you have a positive charge and negative charge here, I think you know how to draw the field line. What about if there's another negative charge? What does it look like? So maybe it's something like this. So all the field lines come from positive charge and go to negative charge, or go to the infinity, and it should be something look like this. Something like that. Sorry, I'm using the mouse to draw some pictures. It doesn't look like very smooth, um, but you know the general direction of the field lines in this system. So when you draw field lines, you just need to remember all the rules or all the features. It starts from positive charge and goes back to either negative charge or goes to the infinity. And they don't cross. Then you can draw the field lines. Okay, now we have introduced the electric field lines. Another concept we're going to introduce is the flux of electric field E. The flux of electric field E through a surface. Now let's see, if you have a surface, close the surface in situation A, and you have two charges, 2Q and Q, positioned inside the surface, then the field lines should look like this. Some of the field lines go out, some of the field lines go to the other charge. Sorry, there is a mistake in the textbook. Actually, this charge shouldn't be Q. It should be negative Q, because field lines always go to negative charge or go to infinity. So please correct the error in the textbook. This is negative Q. So we can define a concept which is flux of E through a surface S. It's integral of a surface for E times dA. That means how many electric field lines are going out of the enclosed surface. And then we define it as a flux of E, which is phi E. So this phi E, or flux of E, is the number of field lines passing through S. If you have positive charge, negative charge, there will be some field lines going out, and also maybe some field lines going in to the surface. However, there should be more field lines going out than going into the surface, because the positive charge is 2Q, but the negative charge is only Q. So for some charges inside the enclosed surface, there will be some field lines either going out or going in. But if the charge is outside the enclosed surface, then the electric field line should go through the surface. It may go in and then go out of the enclosed surface, but the flux should be zero, because any field line which go into the surface will finally go out of the surface. For example, something like this, it will go out from somewhere from the surface. So this suggests that the flux through any closed surface is a measure of total charge inside. Why? Because for for a given sampling rate, the flux is proportional to the number of lines drawn because the field strength is proportional to the density of field lines. So here, um, E times dA is proportional to the number of lines passing through the infinitesimal area dA. And the dot product picks out the component of dA along the direction of E, as indicated in this figure. It is the area in the plane perpendicular to E that we have in mind when we say the density of field line is the number per unit area. So when the area is bigger, then there's more electric field lines going through it. But when you consider the closed surface or closing surface, then the flux through any closed surface is a measure of total charge inside. For example, if there's no charge inside in situation B, then the flux is zero because any field lines go in to the surface should go out at the other end. For the field lines that originate on a positive charge must either path out through the surface or terminate on a negative charge inside. On the other hand, a charge outside the surface will contribute nothing to the total flux because its field lines path in one side and out the other side. So this is in sense of Gauss' law. Gauss' law is describing the relationship between a flux of E and charge Q. So if there's no charge Q inside, then the flux is zero. If there are some net charges inside, then the flux is non-zero. And the flux equals to E dot dA, of course. And then if we consider a point charge Q at the origin, let's see if there's a Q at the origin, the flux of E through a sphere surface radius R is, okay, now let's see a sphere surface with a radius of R. Then the flux generated from the Q should be something like this, right? It's a single charge field lines. So it looks like that. If you calculate the flux, it's the integral of E dA. E is 1/4 pi epsilon 0 Q over R squared, and direction, of course, is radially. Dot dA. Do you remember how to express dA in the polar system? So if you go back to chapter 1, for the surface integral on a sphere, we have introduced the way to calculate dA or to represent dA in the surface, sphere surface, or dA in the plane like that. So for the dA on the spherical surface, it equals to this equation. So it's in your textbook, page 40. If you forgot, please go to the page 40 of your textbook. We have introduced this idea in chapter 1. But the conclusion is that, so dA is something like that, and then you plug in dA here, and this is R squared. Here is another R squared, so they canceled out. So finally, if you do a integral, you will have the value to be simply Q over epsilon. So the final equation is the integral of or the flux equals to Q over epsilon 0. So what does that mean? That means if you have a, okay, so let's make it simple. So first, if you have a spherical surface, the flux of electric field means how many field lines um, are coming out of the surface equals to Q over epsilon 0. So epsilon 0, of course, is a constant of the material. So that means flux for a surface depends on the charge. For example, if you put Q here, you have some flux. If you put 2Q, then your flux from the surface is doubled. So that's the relationship between flux and charge. Now we get this conclusion based on the spherical case. Actually, if it's not spherical, if some surface like that, the conclusion is still true. the uh, the flux on this surface also equal to Q over epsilon 0 because any field line go through the spherical surface also should go through this curly surface. So no matter which type of surface you choose, you will get the same conclusion. Flux equals to Q over epsilon 0. Okay, this is the conclusion. The flux through any surface enclosing the charge is Q over epsilon 0. Now, this is the situation for one charge. If you have multiple charges in a surface, how to do it, how to calculate E. We know if you have multiple charges, then you can calculate the E at any position. Let's say if you have Q1, Q2, if you want to calculate the E at this position, you can first calculate E1, which is generated from Q1, and then E2, which is generated from Q2, and E should be the sum of E1 and EQ. And it's a vector sum, of course, because E1 and E2 are both vectors. So E equals to the sum of EI. If you have multiple charges, you just need to do the vector sum of all the electric field generated by each individual charges. So E equals to sigma EI. I from 1 to n means the number of the total charge. The flux through a surface enclose them all is, for example, if you have surface to enclose the charges, and if you want to calculate the flux, then what you can do is E dot dA, that's the equation of flux, it equals the sum of EI dA because this E is a total electric field. It equals to the sum of each charge generated electric field. So you can write it into a sum of flux generated by each charge. And then it equals to, of course, the sum of Qi over epsilon 0 based on the previous equation here. Okay. So that means if you have, let's say, two charges, Q1 and Q2, and if you want to calculate the flux, which flux of a surface which enclose those two charges, then you can calculate the flux generated by Q1 and then generated by Q2, and then sum them up. You will get the total flux. So for any closed surface, the flux equals to Q over epsilon, and Q is the entire charge or the net charge enclosed in the closing surface. For example, if this is the surface, if you want to calculate flux of this surface, you need to calculate the net charge. If you have 5 charges, you need to calculate the sum of the 5 charges or the net charges inside the surface, and then use this net charge over epsilon 0. If there are some other charges outside, of course, they don't contribute at all to the flux of the surface, because any field line goes out, goes into the surface, will come out from the other end. So it doesn't contribute any flux. And this is the integral equation for Gauss law. So this is the Gauss law. And now let's see another format, which is differential equation of Gauss law. So we know a surface integral could be written into volume integral in this way. This is surface integral of E, and you can write it into a volume integral of del E. And the charges in the enclosed surface could be written into a, let's say, an integral of rho dt. Here, rho is a charge density. Let's see, if you have a surface here, if you have some charges, then the charge density or the charge distribution density is a function, rho. And when you do an integral, volume integral of the charge density, you will have the sum of the charges, which is Q enclosed charges. So because flux equals to equals to the Q enclosed over epsilon 0, and flux equals to this, charge equals to that, this flux equals to Q over epsilon 0, then on the right side, this one should equals to rho over epsilon dt integral. So you can write it into this form. This one, which is here, equals to this one over epsilon 0, which is here. So the Gauss law becomes in this format, but you can see this is a volume integral. This is another volume integral. This is a volume integral for del E. This is a volume integral for rho, which is charge density. And this is true for any volume. So the integral must be equal to, the integrand must be equal. So del E must equal rho over epsilon 0. So here, del E equals to rho over epsilon 0. That means that is the differential form of the Gauss law. Okay, now introduce both integral form and the differential form of Gauss law. The divergence of E. So we have some time to introduce the Gauss equation, Gauss law. So we demonstrate the Gauss law based on the spherical surface. But actually, another way to derive the Gauss equation is if you directly calculate the divergence of E from equation 2.8, which is the equation describes how to calculate E, which is 1 over 4 pi epsilon 0, then Q over R squared dt, of course. So so if you calculate the divergence of E directly from the previous equation, you can try it. You can just derive it purely based on mathematics, or based on your skill of integral. You will finally to prove that again, del E dt, integral of del E dt equals to so the volume integral equals to the surface integral of flux and equals to Q enclosed over epsilon 0. So that means even if you use just mathematics method, still you get the same conclusion. Flux equals to Q over epsilon E. Okay, so here is a reference of some useful equations. You might need some equations in this web page. If you want to download it, you can try. Okay, so that's all for today's class. Thank you and see you next time.